Example 1 on section 4.6. The title of the lesson is Graphing Using Calculus and Your Calculator. So we're going to be using our calculator and calculus. And if you recall from before Christmas break, we learned about increasing, decreasing intervals. We learned about concavity, inflection points, maximums, minimums, that kind of stuff. We also learned about asymptotes with rational functions. This is a polynomial, so we won't have any asymptotes in this one. But all those things are going to be used in this section. Okay, so our basic end result of this section is going to be a very detailed graph that's going to be impeccable with very few points. All right, so that's what I want. Is I want the best graph I can get with the fewest number of points possible. And I'm going to use calculus in order to pinpoint specific x values that are useful to me. I'm going to use algebra to evaluate. So once I know an x value is important, I put it in here, I get a y value that goes with it. That gets me points on the curve. So anytime I want to actually plot points on the curve, I go right here. Calculus is going to tell me what x's are important, and then I go back to y equals to find out the points. All right? And then once I get enough points and enough information about increasing, decreasing, concavity, and maximums, minimums, that kind of stuff, then I'm going to put pencil to paper, connect the dots, and get my nice, very exact curve. I'd say a polynomial function you're looking at probably maybe 8 to 10 points at most, maybe not even that many. I want you to get in the habit of creating an XY importance chart. X, Y, and important. And for the sake of graphing, 2 decimal places is sufficient. Anything beyond that's overkill because, again, you're estimating if it's 1.56 or 1.561, I'm going to ballpark that in about the same spot. So it's not that big of a deal to go extra decimal places on this. But x and y are the coordinates of the points. Important would be maximum, minimum, inflection point, intercept, that kind of stuff. All right. For me personally, intercepts would be something I can find if I need some extra points. Y-intercept's easy. X equals 0. All right. If I let x equal 0, 0 plus 0 plus 0 plus 2 is 2. That's the y-intercept. X-intercept's a little bit more challenging. That's where y equals 0. So I might keep x-intercepts on the back burner. If I need some extra points, maybe I'll find some x-intercepts. Okay. Usually for anything higher than a second power function, I'm going to have to be using my calculator. The graphing function on my calculator, anybody find those? So using a graph in order to find points in order to graph seems like a little redundant to me. So I'm going to stay away from x-intercepts for right now. All right. As far as using calculus is concerned, if you recall from chapter 4.1, we used the first derivative to find critical numbers in order to find increasing, decreasing intervals to establish if it's increasing to decreasing getting a maximum or decreasing, increasing getting a minimum. So the first thing I'm going to do is I'm going to do y prime. I like descending order. You can see the problem's given me in ascending order. So I'm going to differentiate backwards here. So I'm going to do this term first, so negative 3x squared. This term second plus 18x, and that term last minus 15. Section 4.3, we use the second derivative to establish concavity and inflection points. So I want to also get the second derivative, negative 6x plus 18. I do recommend finding the first and second derivative immediately. Put it in a little box. So when you need it, you go back and get the one you need. Because all too often I see people noticing things, changing up problems, and all of a sudden getting the wrong answer. So what you might notice here, hey, everything here divides by 3. Okay? If you divide everything by 3 and keep it y prime equals that, and all of a sudden you change the derivative. Okay? So everything does divide by 3. In fact, negative 3 is what I would take out of that one. But do that after you found the second derivative. 2 times negative 3 is negative 6, 18. Those numbers are important. So if I'm using the first derivative, I want to find critical numbers. Critical numbers happen where the derivative equals 0, where the derivative is undefined, and at endpoints. Those are my 3 criteria. I can see very clearly there are no endpoints in this problem. Polynomials are never undefined. So the only thing I have to care about here is when does this thing equal 0? And again, negative 3 is a common factor. Since I have just a regular polynomial function equal to 0, I can just divide by negative 3. so. As long as I'm multiplying or dividing by a constant, it doesn't change the overall value of the function, as long as it equals 0. If I kept it y prime up here, this does not match that, right? So that's not what y prime is, but again, the part that we care about, the part that's going to get x equaling values equaling 0, is not involving the negative 3, so we can take that out. I can factor this x minus 1, x minus 5. So x is equal to positive 1 and positive 5. Going back to the zero product property from algebra. Once you get factored form equal to 0, what makes that 0? What makes that 0? Positive 1 and positive 5 are the answers. So I immediately know that 1 and 5 are magical numbers in this problem. Okay, that's places where the derivative equals 0. That's places where the sign of the derivative, being slope, if it's positive to start off with, it can switch to negative. If it's negative to start off, it can switch to positive. Okay, so it has the ability to switch sign. So I'm going to set up intervals from negative infinity to the smallest number, from the smallest number to the next biggest number, and that's the biggest number, so we then go to infinity. Those intervals will establish intervals of increase and decrease. Again, it tells me whether the graph is increasing going up or decreasing going down as we move from left to right. And what I want to do is I want to pick values within those intervals. 0 is between those, 2 is between those, and 6 is between those. Nothing magical about those numbers, just any number between 1 and 5 will do. I like 2 because it's smaller than 3. All right? Bless you. My goal is to establish what the sign of this thing is on these intervals, right? Because again, the derivative represents whether it's increasing positive slope or decreasing negative slope. So if I take these test values here, 0, 2, and 6, and substitute them into my derivative, I can establish sign. And obviously 0 is easy enough. 0 plus 0 minus 15 is negative. The other two are a little bit more challenging though, right? So you might want to, if you have to evaluate the same thing for several things, go to y equals and type stuff in. So if I type in y equals the derivative, negative 3x squared plus 18x minus 15, go to my table and type in my numbers 0, 2, 6. Okay. Obviously, again, 0 was negative. Positive 2 got me a positive 9. Positive 6 got me a negative 15. Okay. The number's not as important as the sign. The sign establishes whether it's going up or down. So I know for a fact, because again, the only places the sign can change are at 1 and 5. You can see at 1 it did change, at 5 it changed again, right? From negative to positive is a decreasing interval to an increasing interval. And positive and negative is increasing to decreasing. And if it goes from decrease to increase, it's going to hit a minimum. If it goes from increase to decrease, it's going to hit a maximum. So again, that's what my first derivative does for me. That's what the calculus of the first derivative does. It gives me an idea of the shape of the graph. I know the graph's going to go down, hit a low point. It's going to go up, hit a high point. It's going to go down again. So I already know it's going to look something like that. Okay? I don't know specifically where it's at. Okay? I don't know specific numbers here, but that's the shape it should have. Decrease to increase to decrease. All right? I also know that x equals 1 and x equals 5 are important values. So again, that's what the first derivative also did for me. It got me critical numbers. Anytime you get critical numbers, they immediately go on your chart. And I've already established that 1 represents a minimum and 5 represents a maximum. That's everything the first derivative can do for me. Okay, so once you've done all that stuff, you've established increase and decreasing, you've established min and max, and you got your x values that represent mins and maxes established on your chart, you're done using the first derivative. Okay, I'm now ready to evaluate y. I can do this now or later, doesn't matter, because I can still have to find some critical numbers on the second derivative, right? So take your pick. If you want to do it now, that's fine. If you want to do it later, it's fine. What do you want to do? Later. Later, okay. We'll evaluate all the points later. So I'm going to take all this stuff, kind of shrink it up and stick it over here. That's a good spot for it. Okay, then we move on to the second derivative. Second derivative's function is negative 6x plus 18. Once again, it's a polynomial function. Once again, we're looking for critical numbers. Endpoints don't exist, right? No endpoints. Undefined, polynomial functions are not undefined. So equals 0 is the only thing we have to consider. So negative 6x plus 18 equals 0. That means that 18 is equal to 6x, which means 3 is equal to x. Okay. And again, x equals 3 is a critical number of my second derivative, which means that x equals 3 gets to be put on our chart. All right? And once again, with critical numbers for the second derivative, once we've established all the critical numbers, which the only one is 3, then we set up our intervals starting at our lowest value, negative infinity, up to that number, and then from that number to infinity because we only have 1. Once again, we're going to pick test values, numbers within these intervals. Number between negative infinity and 3 would be? 0. 0 is perfect, okay? You can put negative 572 if you felt like it. I don't, but 0 is perfect. Okay, between 3 and infinity? 4. That's what I would pick, 4. Okay, smallest integer that I can pick. That's my favorite one. Closest to 0 in the case of the ones, because of course negative 572 is smaller than 0, but closer to 0. All right. And again, these test points are testing what the sign of this function is. Is this function here positive or negative? So we're going to go back here to the second derivative to evaluate that. And negative 6x plus 18 we can do in our head, right? So if I put 0 in, 0 plus 18 is 18, which is positive. Negative 24 plus 18 is negative 6, which is negative. So if you can use your brain to do it, great. If it's squared, cubed, whatever, to some higher power, then I would probably use a calculator with the table just to make it easier on myself. What I can see there, it's positive from negative infinity to 3. Again, the critical numbers where the sign's allowed to change, and we can see it did change to negative. If the sign changes at a real value of x, we're going to get an inflection point. So we've established there that 3 is going to give me an inflection point, and we've also established it's concave up. From negative infinity to 3, it's concave down. And notice, concave up to 3 and concave down after 3, that fits along with the increase and decreasing intervals we got, right? So they should match. If we had this picture here and it said it's supposed to be concave down then concave up, all of a sudden they contradict each other, we probably did something wrong somewhere. All right? But just be careful of that. And so again, I've got increase and decreasing intervals, I've got concavity figured out, I've got my inflection point figured out, I've got my minimum maximum points figured out. Everything I need to know about this graph has already been established. Okay? So now I want to go to my calculator, go to y equals, and I'm going to type in the function because at this point I want to start getting some y values. So I'm going to put 2 minus 15x plus 9x squared. Helps if we hit the 9. 9x squared minus x cubed. Alright, verify that we typed it incorrectly, which I did. I'm going to go to my table, I'm going to start substituting numbers in. So obviously 0, 2, we can verify that. 1, 5, and 3 are the numbers we got here. So 1 is negative 5, 5 is positive 27, 3 is 11. So altogether, out of all the calculus, I found 3 critical numbers. Now again, I got a y-intercept because y-intercepts are easy. So I got 4 points. Okay? I'm going to go ahead and put those 4 points to paper to see if I have enough information. Because again, in addition to these 4 points, I also know it's going down and up and down. I know it's concave up, concave down. I know that stuff too. Go to my second page here. And I think I put x at a 1 scale and y at a 4 scale. Yep. Did I do that? Yep. Okay, good. All right, so 0, 2 would be right here. And every dash on the y-axis represents 4, so 2 is halfway up between 0 and 4. 1, negative 5, 1, negative 4, and then 1 more would be about here. That's a minimum. Notice I wrote minimum below it because I know the graph's going to start going up after that. So you can kind of, if you visualize where the graph's going to be, you can kind of get an idea of where you can put the labels. If I go with 3, 11, 1, 2, 3, 4, 8, 12, so 11 be just a little bit below here. That's an inflection point. And again, if you imagine the graph's shape here, it's going to be kind of going along there. I could probably fit IP over there. I want you to identify things on your graph as you're graphing them. Okay, we have 5, 27, 1, 2, 3, 4, 5, 4, 8, 12, 16, 20, 24, 28, so 27 be about here. That's a maximum, so I can probably put that above that. That's all the points I have. Okay. Now, without doing anything else, if I just use the concavity information, Concavity switch is an inflection point. It's concave up to that point, concave down after that. It's going to hit a low point here and a high point there. Okay, so if I just do that, I'm going to use the red pen to do this. There's concave up, there's concave down. That red graph is pretty close to the right answer. It's not perfect. Okay, but all I found was 4 points. It's going to be pretty close to perfect. How can I make it better?
Find more points.
Find more points. And how you find more points, you pick more x's, right?
Yep.
So I can see that 2 and 4 haven't been picked yet, right? So, and if I want to get some more points, if I just come over here and type in 2 and 4, we get 0 and 22. Now notice on the important column there, I'm not writing anything because they're not really important. They're just extra points. Okay? So 2, 0 and 4, 22. 1, 2, 3, 4, 4, 8, 12, 16, 22. Hey, look at that. I missed 2, 0 by just a smidge, you see, but I was dead on 422. Okay, adding those 2 points, it still makes my graph look pretty good, right? And notice on this part here, I just kind of missed that minimum by a little bit. If I hit it minimum right on, I pretty got close to 2, 0. So even adding points in there gets me closer. I could get more points if I felt like it.
6 is 20.
6 is 20, that's doable. So 1, 2, 3, 4, 5, 6, 4, 8, 12, 16, 20. So I missed that one by a little bit. I can even go with halves, because again, my calculator is doing all this calculating for me, right? So if I go 0.5, 1.5, 2.5, and so on, those are all doable. The extra work involved for you is just typing extra numbers in. You might get a little cramp in your index finger if that's the one you use to type. 0.5, 1.5. If you get a point you don't want to graph, you can just skip it. And all those points, negative 3.375, negative 3.625, and so on, those are all points on the graph. So negative 3.38, negative 3.63, 5.13, 16.88, 25.63, and 25.38. I plot those points. 0.5, negative 3.38, almost negative 4. 1.5, negative 3.63, about here. Getting kind of close there. 2.5, 5.13. 5.13 would be about here. 3.5, 16.8. 4, 8, 12, 16, 17 be about here. 4.5, 25. 4, 8, 12, 16, 20, 24, 25, probably about here. And 5.5, 25.38 about here. Again, that red line represents my initial stab at it with just 4 points. Those other points are hitting pretty dead on it. The only one I missed by a lot was this black one, so I got a little carried away. So maybe if I wanted to fine-tune this a little bit, I can just kind of fine-tune a little bit. All right. So again, the point is, as few points as possible, but you still want to get a decent graph. Polynomials you're looking at in the area of like usually 7 to 10 points is sufficient to get a pretty decent graph. The values you pick are up to you. Okay, so once you get your magical numbers here that calculus does for you, once you get those, everything else, if an x hasn't been picked, it's fair game. Okay, if I picked 7 and it gave me like some ridiculous number, I can just throw that one out. Or let's just say, well, I want to pick 8. Oh, I don't want to graph negative 54, so let's just not graph that one. Okay, so skip it. All right, so you have that freedom. If you pick one that gets you some ugly number that's way off the chart, then just throw it out. It doesn't have to be graphed. But graph enough points that you can get a clear picture. You can see the concavity. The concavity switches the inflection point. You can see the decrease to a minimum, increase to a maximum, decrease again, and see all the stuff that's supposed to be happening in the graph. get a good sketch of the graph with enough points to create the proper picture.